The next chapter from the TAPR Digital Communications Conference of 2018, given to us by Steve Gunderson. Coming up. Hey, good afternoon. My name is Jason. I'm KC5HWB. If this is your first time here to join us, please click on the subscribe button below so that you can keep up with all the videos that we post on this channel, anything that's new in amateur radio. This is the next episode from the TAPR Digital Communications Conference of 2018, titled Implementing MACA, M-A-C-A. It's an acronym. We'll learn what that stands for later. Implementing MACA and other useful improvements to the amateur packet radio for throughput and capacity. I admit I have no idea what this was before I watched the video. So if you're interested in packet radio, APRS and the like, take a look. Let me know what you think in the comments, and thanks for watching.
All right. Next up, we have Stephen Gunderson and his co-author John Bonnett, is it correct? And implementing MACA and other useful improvements to amateur packet radio for throughput and capacity.
Good afternoon. Let me introduce myself. I'm Steve Gunderson. I got involved in what's called disadvantaged communications back in the early 90s. I committed to supporting non-government organizations and overseas. The communication costs, telecommunication costs were killing their budgets. And so we committed to do compressed email and other types of things, reduce their costs. We successfully did that. We reduced the telecommunication costs by a factor of 4 to 3, somewhere in that area. So for somebody that was living overseas at $300 a month for their budget, they were spending $1,000 a month on telecommunications costs. As an outcome of that work and teaming up with people, I'm a Navy civil servant and I'm in research, so that's the bulk of my day job. I got teamed up with the U.S. Marine Corps as they were looking at over-the-horizon communications, all digital. They were looking into the year 2010 for an all-digital battlefield. And I got teamed up with that through the Marine Corps Warfighting Lab in Quantico, Virginia. I was one of the original 5 guys on that team. And it was all data. It was land mobile radio, hooked up to the global command and control system, forward observers, but it was all data. And we conducted that experiment in 1997. It was successful. That approach was used in 2005 for a military event in Afghanistan. Okay. Now, after that, I got picked up. I met Motorola. They were developing their Iridium satellite. So they gave us specifications for a protocol for compressed email for the Iridium satellite. Also worked with Inmarsat. So we did that. And then Codan HF out of Australia for the UN World Food Program contacted us, and so we did adaptations for that. That system's installed in Turkey as their emergency communications network for the earthquake disaster system. So that's the foundation for all of this. I'm going to talk about what we started doing in the late 2000s. Okay, we're going to talk about the project. I'm the project manager for the communication methodology of last resort. We're going to talk about a lot of the technical stuff underneath the hood for this. Okay. I live and was born on the California coast, all the way from San Diego all the way to San Francisco. There are California missions. We have earthquake faults. We have floods, fires, everything you name it, we've got it except for hurricanes. Now, what's happened is they have extensive packet networks. There was UOSI grants, there was pre-existing stuff, a lot of 1200 baud, and a lot of it's installed in EOCs, fire stations, police stations, hospitals. And they're using Outpost and WinLink 2000 messaging software. What was initiative for this project is in one of the counties, there's CERT. It's everywhere. And they run OK drills. People place OK signs throughout communities. CERT teams do neighborhood surveys. They count the signs. But they've also added triage signs consistent with their thing. So what happened was the Office of Emergency Services wanted to get that information to their EOC. They wanted to know what the status of the communities would be after a major disaster for situational awareness. Oh, let me go back. Wrong button. Okay, for situational awareness. So that was the beginning of it. So what they did is they stood up this project, and so it was emergency data communication. So the underline had to be data. They didn't want any voice, and they wanted data because it's faster and more accurate. Okay, here's the 3 primary objectives. They wanted an independent system. They didn't want to use cellular or any of the other systems. They wanted it interoperable with what they had. They were pulling out the analog LMR radios, and so they wanted that to work on that. And of course, make it work with what we have. They didn't want to buy anything new. Okay, what we did was we did an initial first demonstration. John Bonnet, KK6JRA, did this. He lashed this together in a matter of weeks. A lot of the hams were using depiction mapping software at the time. It was a budget system. They were using it for location properties. Again, OES wanted to know where the problem was and what the problem. So John took the thing off. Depiction worked with email, stripped off the header, turned it to XML, which was just a text body, placed it in an APRS packet, pulled it back out the other side, put an email header on it, handed an email to depiction, and that all took about 3 seconds to transmit, including an ACK. So we reported that back to the committee. They said, hey, we like that. See if you can get that up over the mountain. So after the project started, what we did is we started benchmarking the current state of the art. Okay? This is from WinLink's 2000's website. This is their Q&A, FAQs. 2 minutes at 1200 baud. 9600 baud, 1 minute. These are long times. There's anecdotal data from a number of other counties that demonstrations to public safety professionals took about 1 to 2 minutes to send useful data, say from a fire station. That is not really that great. Now what we also did, let me explain to you this ideal speed. It came from a SATCOM, so ideal speed is the bit rate divided by 10, and that is for a bidirectional, full duplex, high latency satellite link. So we're benchmarking to Iridium and Inmarsat is the speed. So the throughputs there were pretty low, and compared to the theoretical, about 7%. Okay, that's not really that great. So what we did is we took Outpost, we just did the simple baseline that way. We ran tests. Outpost was a little faster and a little bit higher throughput. Now let's talk about what's going on here. These all use the connect command for reliable transmission. That's the standard setup. So this is the baseline of way hams work right now. We're seeing these up and down the coast. Okay, so let's talk about additional tests. We're going to do some different things. So here's the 1200 baud for Outpost and WinLink. We assumed the frame size was 4 default for, say, a Cantronics modem. Here's their sizes. Here's the speeds, the throughputs. Now what we did is we turned off Connect and went to Unproto, just as we did with our initial demo. And we tried different frame sizes, larger frame sizes, different file sizes, different amount of compression. We used a different compression in WinLink 2000. We used zip. And look at these speed increases, just switching to Unproto. 2x, 3x. Now, for a simplex link, 84% compared to a high latency satellite link is excellent. So it is possible at 1200 baud to get easily just changing modes, increasing packet length, and doing some other tricks that we'll talk about, 2 to 3 times faster. You're not going to get much faster with it. It's pretty spectacular. So that's the summary of what I just told you. Now what we did is we defaulted 256, frame size is 16. We send 1 ACK per 4 KB. That would be a good size message for an email message, okay? And you can get some pretty good performance with that. So let's kick it up to 9600 baud, again, Unproto. We're going to compare it. So there's our connect command. Same things, 67 characters a second, 1 out of 14. outposts a little bit faster. So those are our benchmarks. Okay, what we did is we started working, now again, this is what we have, so we were used to Cantronics, TNCs with a variety of different radios, Kenwoods, Motorola Professional, different packet lengths, and getting 6 times up to 12 times faster. We have one test that got up to 920 CPS, but we had fans on the big Motorola Professional radio, so it wouldn't melt down on that test. Now, the other thing is we have a lot of the Kenwood D710 radios. They're installed in the hospitals. It has a built-in TNC. It's a good, solid radio, and it's a little bit slower, but it's still very good. For the convenience, you don't have to calibrate the radio at all, and it appears to have very good packet loss factors there. We think that they may be doing some tricks inside to improve the error rate. We don't know exactly what they're doing, but that's worth looking at, okay? So, now, here's the bottom line. Using this, we're getting the expected several-fold throughput. It is going several times faster at 9600 baud. So let's talk about the protocol. Okay? Now, we call it UX25 after Unproto AX25. So we're going to work all Unproto. Okay? Now, this again is John Bonnet's handicraft here. Okay? We're following APRS. We're not changing a lot. We're running them as experimental APRS packets. This all runs, okay, AX25, we are not changing AX25. That's the outer wrapper. It's basically the RLP, the Radio Link Protocol. Provides the fundamental addressing. Inside, in the data payload, is a secondary header and data. So it's an applique. So this can be run on any packet system with any hardware. So this is the AX25. These are the payloads, and there's 3 different types of commands. Now the whole trick is you want to minimize this overhead. So the maximum is 6 bytes. So out of 256, you have 250 bytes. Okay. Now, format, again, commands are very simple. You just have the APRS flag bit, like byte, load some data in there, and the carriage return for the close. You have different simple commands. They're just simple English readable, ASCII readable commands. Nothing special about that. Humans can read that. And then for packets that you send to specific stations, you can ask the repeater to send a broadcast message, who my call signs are, and some of our early experiments with CERT. And you can send mapping elements. They're very simple. And so this is all basically ASCII. It's readable. Now this gets to be a little more fun. The message format, the secondary header includes addressing, sequence numbers, and type. These are reliable. So this is the format inside, and you have payloads. So commands you can have, and these are the 2 key packets that we're going to talk about relative to MACAs, the synchronization packet and the send yes, send no packets. Again, now these are single bytes here, so what you do is you put a command as a single byte and they mean something. You can have login, snacksax, and into file. Okay, so that would be 1 to 4 packet type messages. Now, this is the most important packet. This is the synchronization packet. This precedes file transfer. So if you're sending compressed email, this is the thing that does most of the work. So it's core. It does multiple things. The whole thing is avoid lengthy session protocol exchanges. This is very common in the internet. If you go to POP, SMTP, anything like that, you have a constant dialogue back and forth. On a simplex link, where you have RxTX turnarounds, that takes a lot of time, really slows things down. This is actually a format here. This is an actual snippet out of the code. So you have a login process. You have a UUCP file transfer codes here. Then you have things for packet and for how long things are going to be, and then back to the UUCP. So it's a long packet, but instead of having an exchange back and forth, one packet. You can do everything that you need to do. Okay, this is a file transfer. This is an eye chart, but this is actual source code snippet. So it's very simple. You have a start, a sequence number, which is 2 bytes. What type of data are you doing? You send the data, and then you have a character return at the end. Again, it's very lean, so you can send 250 bytes in a 256 byte packet payload, and it's very efficient. Now, I'm going to talk about some of the other things that are done. It's not up here on the view graphs. What we do is we encrypt the data. No, we compress the data with zip. So it's up to 4-to-1 compression. And then we don't UU encode it. We base 64 encode it. So it's the same thing done for multimedia internet exchange for attaching files to email. That way you can optimally pack the packets right to 250 bytes. So how does that relate to this? Okay. First thing, MACA is a media access control for amateur packet radio. Amateur packet radio uses Aloha net, so stations transmit when they want to transmit. The extension that amateur radio includes is carrier sense. So the radios listen for other transmissions and won't key the transmitter if the channel is occupied. So they listen for this, but the fundamental thing here is the stations decide when they transmit. Not a repeater, the stations. If they don't hear, they try to be polite, but they may not be able to hear all the rest of the stations. So if somebody's on the other side of the hill, or if somebody's out of range, they may not be able to hear this. So they may transmit when somebody else is transmitting, or they may not transmit when it's okay to transmit. So MACA was proposed at the 9th annual conference as a solution for this. So let's take a look at what this looks like. First problem it addresses is hidden terminals. So let's say we have stations on either side of a hill with a digipeater on the top there. This guy is talking. This guy wants to talk. They talk at the same time, and somebody's going to win on that. But they don't know that the other station's talking. The more subtle problem is exposed terminals. Say this digipeater is now talking to station A. Station B wants to talk to station C, which is out of range. But it hears the channel is busy, so it thinks it can't transmit. So, the solution that was proposed by Phil Karn back in 1990 was to use channel pilots. So you request to send, and then you receive a clear to send. Very simple. Very elegant process here. So this is a case where station A transmits up to a digipeater that says you're allowed to transmit. After that happens, after this permission, it starts sending data. So it's allowed to do that. Now let's say station B comes online. It doesn't hear this, and it wants to transmit. So it transmits an RTS, but the digipeater does not answer it. So it doesn't do any additional transmission. It doesn't get the CTS. It doesn't transmit. It doesn't jam the channel. Now, one thing is, let's say this station is a little bit closer than this station, so the FM captures that, then this guy might lose a packet, but that's recovered. Okay. Now, what happens is this station is going to wait until it gets a clear to send. So it's very polite, and it works. So what we're going to do is we're going to talk about what happens when a more complex network. And what happens is that these RTS, CTS include file sizes. So there's a time estimate. So let's look at a sample here. Station B transmits up, gets a clear to send. Station D hears the initial RTS, and it hears the repeater's response. So it knows to stay off the air. It keeps silent. These two stations hear one side of the communication. This here's the RTS, this here's the clear to send, but they know because of the information of the file size and number of packets to stay silent. So they do not interfere with this work right here. So they wait and they don't send any traffic. They wait until an estimate. They don't have to wait until the channel is clear, and then they can start sending their RTSs. So MACA uses a request to send, clear to send. The UX25 protocol that was mentioned earlier uses the sync that is equivalent to RTS. The send yes is equivalent to the clear to send, but it also includes this. We'll talk a little bit about this, and it includes the estimated number of packets that will be transmitted on the channel. Now again, what they have here, the transmit time estimate, there is a file size, and in case of UX25, there's file size and packets. And this is transmitted on these to allow other stations to estimate how long to stay silent. This is only used for larger transfers. This is not used for short transfers. So, the UX25 that was used to improve throughput implements MACA functionality, and the key to this, making this work, was to use unproto. In other words, other stations listen to all the handshakes and all the transfers of stations, other stations. So if you use a connect command, they're ignoring it. If you use unproto, then it gets it. And so you're not dependent upon carrier sense because you're monitoring these handshakes. Okay, because of these things, there's other useful improvements. There's things that can be done other than just avoiding hidden terminals and knowing when not to transmit. Okay. Again, stations in the current architectures decide when they transmit. This works great for APRS, lightly loaded networks, short packets. If you have a heavily loaded network with mixed traffic, it doesn't work as well. And the digipeater itself doesn't know what's coming in. In other words, somebody can transmit and you don't know how much is going to be transmitted, who's transmitting, you don't know any of that. That's what carrier sense. You don't get useful information to control the network. Now, the radio amateur community solved this problem on their voice nets. You have sophisticated scripts. These are media access controls. Stations check in, they identify the type of traffic, how long it will be. Network control either grants or doesn't grant permission to transmit. You guys are very good at this. Very good at this. And there's always a tempo to it, listening to it on the air. The other thing that happens is short breaks are reserved there so that stations can break the net. They can get in with higher priority traffic. And this is very useful for the type of situations we're looking at for the CERT surveys. Okay. So this is really the first conclusion. MACA is the foundation for adding directed net principles to amateur radio, amateur packet radio. You implement MACA, you can do this. So that's a collateral benefit of that protocol. Okay, UX25 extends it. It sends no. Stations can be told no. That's very important. You just don't say yes, or just by omission, because it doesn't know if it didn't get the packet. And what happens in this architecture is it flips it around. Instead of the stations deciding when they transmit, digipeaters decide when stations can transmit. This is a complete inversion. This is the way Wi-Fi hotspots work. MACA is included in the Wi-Fi specification. It is taught at university level. Every wireless networking class teaches MACA. Okay. So, now there's some other things people ask, well, what about simplex? What if we want to send directly? You can do this. Simplex stations, instead of going up to the repeater and back down and using a lot of the channel, can just go straight across. The digipeater can listen to their RTS, CTS things. They can listen to the stuff and they can decide when the coast is clear. This needs to be tested. The other thing is, you don't do MACA, you don't do RTS, CTS for single packet transfers because the overhead's too high. And give you an example, 9600 baud, 250 bytes, so if you, let's say it's 300 bytes total, you're on the air for less than half a second. You know, a fraction of a second. So if somebody sends a critical single packet message, it's a click. And 1 KB messages, 4 packets take less than 2 seconds. Okay, we're going to shift here. Now, this is John Bonnet's kind of his soapbox. Brevity. If you're working emergency comms, keep it brief. Don't send an email. Okay? Human nature, all traffic's urgent priority. Make sure my message gets through. We think message size is a natural way to prioritize traffic, and single packet messages can be reliable, which is critical for emergency communication. So if somebody says, this house is on fire, that can be reliable, okay? Let's go up here. That notice is on Cal OES's website as an example of an excellent message. I received that message on my cell phone on December 4th last year at the beginning of the Thomas Fire. 20,000 people evacuated in a handful of hours. The fire traveled 14 miles in 3 hours and started above a farm and was burning the back of City Hall 3 hours later at the conclusion of a city council meeting. And that was that mayor's first city council meeting. Okay? At that time, that fire grew to 280,000 acres. It burned across Christmas. It became the largest fire in recorded California history. And not only did it burn national forest, it almost burned Ventura down. The power went off through a third of Ventura County for almost all of the evening. Fortunately, the cell phone network stayed up. Fire continued into Santa Barbara County, burned across the mountains. CAL FIRE threw 8,000 personnel at it to stop the fire before it got into Santa Barbara. They stopped it. But a few weeks later, a storm came by, dumped a half an inch of rain in 5 minutes, and the mountains slid in the city of Montecito. I'm sure you've seen the pictures of it. Okay? Let's get back down to this. This is a notional thing that we're proposing. 1 packet, same size as a text message. Let's make it emergency. First, you just transmit it. MACA doesn't get you anything. Same thing for urgent. Priorities can be a little bit longer, and so you're into 1 to 2 seconds transmission time. And you can, if you can't send useful information in half a page of text, you need to revisit that. And then just make all the email routine and let MACA control that when they can transmit and hog the channel. Again, that's 14 words, 101 characters. So we can be brief. Okay. Now let's flip the coin. Email. Why do we use email? Two-part addressing. It's easy to use. Everybody gets it. Everybody's using it all the time. It's excellent. It's not a call sign. It's a user at some place or some organization. But it's inefficient. Email headers can be hundreds of bytes. So if you want to say, house on fire, 3 words, you sent 300 bytes just to say that. That's not very efficient. So what you want to do is to send a one-packet message reliably through the system. So the next thing that we did is we added directory services for messages. We added this type of addressing for messages. So users don't have to learn arcane things. They can just type user at domain without all of the overhead. But they have to keep it brief. 250 bytes, 500 bytes, whatever. So the directory services provide secondary source and destination addresses. These are inside the data packet. And these are 2-byte addresses that reference a directory. And they can reference call signs, domain names, individual accounts, and groups. So they're not limited at that point. The call signs are, hold on. I've been accused of being Italian, but I'm Norwegian, waving my arms around. Okay. I lost my place there. Let me just move on. Okay. Okay, directory services. So what happens in the system here, okay, the primary address, which is the AX25 packet, has call signs in it. That's required. So the secondary addresses in UX25 contain additional information that can identify specific individuals. Okay. These directory services are hosted up in the repeaters, the digipeaters. Okay. So this is another overlay inside of it. So what happens, stations check in, but then they start sending up their local accounts, their domains, information up. That gets distributed to other stations that get check in. So the main common directory is up there. Now the benefit of this for short messages, it makes it easier to use for people that are not skilled in amateur radio. Okay. Now the DCIO of the county wanted this. He wanted trunked packet. He's got land mobile radios, he's got dispatch centers. He wanted this data to work across all the high sites as they move around the county. We have a lot of mountains, a lot of valleys, we have rivers, we have earthquake faults, we have islands, we have national forest, all up and down the coast. So what they wanted to do was have this urgent data comms automatically flow up from mobile terminals and from CERT neighborhoods. Flow up through the network and get here. Okay? So what is supported by this, kind of an extension of directory services, and directory services will operate at the message level. Everything is at the message level. There's automatic handoff. So you don't have to predefine routes to get information from point A to point B. It just happens automatically. Again, it's like directory services. So again, quick summary, stations check in, they do that. Message traffic is, so this is not packet, this is message traffic, is forwarded to the closest digipeater. They coordinate, And then if they move out of range of one there, then it moves across, forwards the messages to the next closest digipeater. So it's transparent to the user as you use it. Again, it's message level, and one of the advantages is if you can batch messages and then compress, so you can get much better compression, increase the throughput, and it applies not only to email, but to short messages. And you can apply multiple addresses to a single message. You don't have to resend it over and over and over again. And you can have inside network and outside network addresses. So it's quite versatile. And because it's all inside the packet network, you don't need to go outside the network for this to work. It will just work on its own. So if you lose an outside link, you're still up and running because they're fully capable smart hosts. They can plug directly into the internet, or they can plug into, say, a county email server internally and then send messages up to county public safety through their networks and back down. So let's summarize. Okay? Here's the conclusion that I have. Amateur packet radio is well suited for this application, especially if it gets faster, especially if they can get the addressing down to a single packet message. Okay? Get it between the communities and public safety. So move it out into the communities. Get it away from the police stations, the fire stations, move it out to neighborhood centers, to churches, schools, libraries, whatever. That way the community can send messages in during a disaster situation. Got several fold increase at 9600 baud just by changing the unproto and extending the packet length. And if you go from 1200 baud to 9600 baud and then do the packet extensions, you're 20 times faster. I'll give you a comparison what 20 times faster is. That's the difference between walking and driving a car. Okay? Do you want to walk there or do you want to drive there? That's a big change. Okay? MACA embodied in this, plus the directed net. You can solve stations hogging the network and away from priority traffic, and it solves the hidden exposed terminals, which is critical where you have a lot of geography. Okay, directory services gives you per messages two-part addressing. So it's brief, it makes it so you can be brief and make it easy to use. That's essential if you've got people coming, especially if you're working with the Red Cross or something like that, okay? And some of the other NGOs. And then for trunk packet, this can totally work automatically. Turn it on. Yeah, I'll give you a scenario. Let's say one county, you got adjacent county. So I live and work in what's called the tri-counties along the California coast. And let's say the southern county has a problem, and so by mutual aid between another county, people come down, radio amateurs come down, they're going to assist. And then what they do is when they get into town, they call in on the voice repeater, say, I'm in town. They say, okay, go over and put your data over on this digipeater frequency. It checks in. They say, okay, you're ready to go. It turns it on. They get the full directory services. So they can interoperate digitally with data. So, I'm sorry, Phil, but this is a direct quote from your paper. Okay? The italics were his. That's not my italics. Okay. I believe the amateur packet radio, if it's upgraded for greater speed, greater throughput, easier use, is very useful for these types of situations, especially when amateur radio is assisting the community, especially CERT teams. Okay. Any questions? Yes, sir.
Actually, I just thought of an enhancement during your talk here. Well, first of all, you're still sending everything uncoded, right? I mean, this.
Yes, everything's uncoded. It's compressed, and then it's.
But it's not forward. There's no forward error correction, right?
Okay, the forward error correction. We're working over existing Cantronics modems.
Okay, the reason I say this is because there are still possibilities for collisions even with MACA, because the radios are half duplex.
That's
you
right.
might transmit on top of somebody's CTS and miss it.
That's right.
For example. So if you use forward error correction that's designed for fade resistance, which you want to do anyway in a mobile environment, and if you make the fade resistance longer than the length of an RTS or CTS packet, then somebody could step on a data transmission with an RTS CTS and you would get both.
That's right. This.
Of course you do. Of course you do.
Yeah, but the professional systems, and so let's say we look at P25 or any of the amateur radio digital systems, are running a 4FSK at 4800 symbol rate, 9600 baud. They run like a 3/4 FEC on top of it, so you're down to 7200 at that point, but it's far more reliable. So it's a trade. So what the professional systems do that. So you slow down, but it works further and with much less error.
The alternative is to make the signal wider and go at the same speed and use less power.
That's right. One of the things, I like to reference the previous paper on LoRa. I looked at that in my government hat to send quiet, secure communications through high link path loss, say through forests, especially in the eastern seaboard. And one of the things that was very attractive was to operate it down at 2 meters, which the chips support that. I also looked at running it at 220 for amateur packet radio, but the synthesizer doesn't support operating on that frequency band. Maybe the newer chips do, so you would have to do a frequency converter or a block converter to do that. But the link benefit improvements. Now, one attraction, you asked that question, Scotty. I saw a band plan for 219 to 220 that was divided into 10 100 kilohertz channels. That's ideal for LoRa. You can configure LoRa to operate in 100 kilohertz channels. And the other thing that was really useful for that is you've got spectrum reuse. You can have narrowband people working there that won't hear the LoRa, and LoRa will ignore the narrowband transmissions at the same time. Spectrum reuse, I'm just going to do a little thing. I'm one of the Navy's experts in ultra-wideband. And I've been on study groups, and we have systems that we've built. We've tested them in the Pacific Northwest. I think it's just glorious up there around Island County and the San Juans. I've spent a lot of time up there at the Naval Air Station. You know, God's gift to that part of the world. And I ended up working with NTIA. They did the spectrum test for us. That was quite an interesting effort there. But the big argument is spectrum use. Can you do two things in the same spectrum at the same time? And it was very controversial inside the FCC. Needless to say, NTIA, I know the people that were involved with it, they were all in favor of it. They were looking at spectrum reuse, and I had a chance to be on a panel with FCC on one end. That was, you know, their viewpoint. I was spectrum reuse on the other side of the panel for DoD, and it was an interesting discussion following that. But spectrum reuse is a valuable thing. So the hams could do this. They could try LoRa and try to test spectrum reuse. And that is consistent with some policy perspectives in the U.S. government. Yes?
Yeah, the main thing, and I've been harping on this for literally decades to try to get this message across, Spectral efficiency and narrowband are not identical, okay? There's this fetish for going narrower and narrower to quote-unquote increase spectral efficiency. That is exactly the wrong thing to do.
That's right.
You need to go wider so you can have signals that require lower, more interference tolerant.
Yeah.
And you combine it with something like this.
Yeah.
Okay, that's how you get efficient spectrum use.
That's
You got to go wider and more and smarter, not narrower.
Yeah.
We can show that. We hams have the freedom to show that.
Yeah. Now, CDMA requires power control to get the spectrum reuse. So I see that the narrowband and, say, the LoRa are so orthogonal to each other, you should not need power control. Yeah.
On the narrowband versus LoRa question, when I was working on this stuff, I put the monitor mode on my FMHT, and maybe when I was transmitting, I heard a little bit of a sound, but it didn't key it up or anything.
Yeah.
So there is some coexistence possibility just from my personal experience. Just throwing that in because just something I noticed. I was curious about it.
On that, we have a bunch of university students here, right? Okay, I'm going to propose a project for you. Okay? Okay. Get the LoRa chips. Now, the available ones operate on 900 band. You can get chips down at 174 also. Build a frequency converter, convert it to the 220 band, 219 to 220. Build a board, and then start running those type of experiments at 220. That would be a very exciting experimental project and would make a great senior project in a university.
They add delay tolerant network capabilities.
Yeah.
Something else, yeah.
Yeah. So I'm just proposing that to, your school. I went to Cal Poly San Luis Obispo. I would have picked this up as a senior project and done it, but I'm not an RF guy. My dad was the RF guy. I'm a linear audio guy. Okay? I learned electronics out of the radio amateur handbooks when I was young in the late 50s, early 60s, but I fell in love with audio, and I set my goal to design the world's best audio gear, and I got my dream come true. I designed the world's first vacuum tube compact disc player. Okay.
What do we have to do with our little digipeater to do this stuff? We've got a little bitty thing up on a hilltop with no internet connection or anything like that.
Okay.
And then who's be able to use it when we do that?
Okay. This, again, another set of experiments, okay? Contact John Bonnet. Okay? This runs on Raspberry Pi. This runs on Windows, OS X, Linux, and Raspberry Pi.
Yeah.
Okay?
Okay.
Put a Raspberry Pi up with your existing packet system. You can just have regular Cantronics, TNCs, KPC3 pluses, 9612s, or if you have the Kenwood D710 radios, use those. Get the little Raspberry Pi, get the software from him, set up some other stations. One of the things we're looking at for the CERT teams is how do we get it in a vehicle for a mobile incident command post. Comfile out of Korea has a little package Raspberry Pi with a touch screen on it, all in one unit, runs off 12 volts. So we're going to be looking at doing that, and they cost $300. So that would be a nice package unit that you could put on a mobile team, and then you could talk to the digipeater with this. So I would encourage experimentation. I think that's consistent with amateur radio's ethos.
And that's all the time we have.